From vectors to matrices, how pure state density matrix revolutionized quantum physics. So in this problem, 12.5, following up on the last problem where we talked about the density matrix and checked certain properties of it, we now have an example of how to make one from a given state. And so 12.5 tells us to repeat the example 12.1 for an electron would spin down along the y direction. And in example 12.1, this was in the standard bases E1, which is 1, 0, and E2, 0, 1, representing spin up and spin down along the z direction, or equation 4.149, construct the density matrix for the electron with spin up in the x direction. So again, what we're doing is changing this direction for the y direction, okay? And we want spin down. Okay, so why do we care? Well, much like before, we see the advantageousness of the density matrix formalism, and although it's kind of clunky right now, it still encodes all the information we need for the states themselves and how they're entangled. That being said, based on the feedback from a couple videos ago, the connection that we have for this formalism to the real world or application is that this is helpful in quantum information and communication. Okay, the density matrices are essential tools in quantum information theory, enabling the description and analysis of quantum states used in quantum computing and communication protocols. So if I know what's happening in whatever given state and I can manipulate the matrices, I can get out the new expectations, things like that. Pretty cool stuff. That being said, the challenge here for this particular one is that we're dealing with pure states, okay? And pure states are a lot easier than that of the mixed states, which are more intensive, which we'll see in a couple, I think two questions. We'll see a mixed state question. So hang around for that. That being said, pretty much everything is in the video. It's a pretty short question, but if you want the PDF, that too will be posted to the Patreon page. Or if you want, I can comment or you can comment and I'll send you the link directly to your comment. Whatever works for you, we can figure it out. That being said, before we jump into today's topic, you should know that my goal is to break down complex physics concepts using exercises from top books. If that sounds like something you'd enjoy, hit the subscribe button and join us in exploring the universe. Now, let's dive in. Okay, so for stop number one, what we first have to do is, recall what the actual spin state was, okay? This was given from 4.32a. So addressing this problem requires that we recall the spin states along the y direction given by 4.3a, which presents a two-dimensional vector state, okay? We're not just 1, 0, and 0, 1. We're actually a mix between 1 and negative I with the normalization factor here, okay? Now, when we derived these from the spin matrices and things like that, that took quite a while, so please go refresh on chapter 4 if you need to. That being said, we know that to construct the matrices elements, we have to have both the state and its adjoint. So let's go ahead and take the conjugate transpose or the dagger. And then what we see is that flipping this ket to a bra, we have to take the conjugate transpose. And now we see that we have both terms that we need. So with this done, let's jump into constructing the matrix. Okay, so following the approach in example 12.1, we'll employ the standard bases outlined in equation 12.21. Given that we're looking for a two bases vector in a two-dimensional space, our solution is going to involve a 2x2 matrix consisting of 4 elements. Okay, that makes sense. To proceed, we'll begin by applying equation 12.16, which allows us to integrate these bases with the given information from the state. So that being said, the matrix elements needed are all of these. That together forms the density matrix, which this is 12.61. Now, each of these elements, say for 1, 1 or ij, is standard bases 1 or I, standard bases j. And in this case, our first element is 1, 1, so we just need 1 and 1. Okay. And to recall, just like we kind of talked about, these came from equation 12.21, which we're told about in the description or the problem statement itself. Okay, so now that we have the bra or the ket and the bra here, we go ahead and put them in position with multiplying their bases directly. So 1, 1 and 1, or 1, 0, 1, 0. And now we see that we have 2 of the normalization factors, so that gets squared. Now we just have what looks like a dot product inside, which makes sense because this is an inner product and an inner product, so they should both be scalars on the outside whenever they're done computing. So 1 times 1, that's our term here. 0 times -i, that's our term here. 1 times 1 here. I times 0 here. Pretty easy. We see that the square and the square root here destroy each other. 1 squared is just itself, so we're good. Now we see that we're left with 1 here and 1 here. So you multiply 1 times 1/2, you get 1/2. And that's pretty simple. That's all we have to do. Now we just need to do the same thing, but we change the E2 bases over here to, well, the second bases to E2 and E2 down here. So we'll have the involvement of E2 and all the rest of these elements. So let's get to it. All right, so our second element, 1, 2, we have standard bases 1, standard bases 2, and the states given here. Run it through the same thing. You see that now you get I over 2, pretty easy. Do the same thing for 2, 1 to switch the locations. Now you see you get a negative I over 2. That's pretty cool. And as you see, whenever you start chugging these through, you'll start to see that these patterns of why the trace is 1 or why they are the Hermitians, why these matrices are Hermitian, start to come through when you start to see how these off-diagonal elements act. Finally, when we have the 2, 2, we have E2, E2, so 0, 1, 0, 1. Take the normalization, square it, conjugate transpose, pretty much the same thing. The zeros really help us here so we can take care of a lot of the computation that way. So we're stuck with 1/2 here. So putting it all together, we get rho equals all the elements, put all the elements in position. We see that we have a 1/2 on all of them. So 1/2 can be factored out. So we're left with the density matrix of 1, -i, and then that's our original state, if you remember, and then I and 1. So what this does is it puts together all the ways that we could have these two corresponding equal states, right? We know that we can be entangled with 1 and -i, but we can also create the same eigenvector by letting the free variable be I here and then making this one a 1 here. So that's pretty darn cool that you have all possible combinations encoded in this density matrix. That's pretty darn cool, okay? And we saw how we could construct the states a couple questions ago, or rather that we will see that. I'm still covering the appendix now for the linear algebra side, so at some point these do come up over again, but nonetheless, whenever you get back to eigenvalues, you see how we're in some superposition of these two, and that's what's really important. That being said, we're about midway through. We did reach our checkpoint of creating this density matrix, so comment with your thoughts below. This stuff is really interesting and not really self-evident initially, but once you start diving into how it's constructed, then you can see how PDP inverse, right, when you're diagonalizing things and you have eigenvectors, eigenvalues coming together, form something unique like this. Pretty darn cool how it's so self-consistent. All right, so stop 2, well, in this case, we have a actual pretty cool equivalent way of finding it from equation 12.14. And that's by defining the operator as just the projection operator from the two states, or the outer product without any reference to the given states. That being said, we see the normalizations, they get squared again. Now we have the outer product of 1, -i, and 1i. Run it through all the algebra there for matrix multiplication, and you get the same thing. That's pretty useful, okay? We just don't know what it's being impacted on, so by telling us that we have bases E1, E2, which are the standard 1, 0, 0, 1, that was easy to manipulate and easy to calculate. Pretty straightforward. That being said, the checks that we could run on this are the idempotent identity, which if we square all these, we get 2 inside, but since we have a 1/2 squared on the outside, factoring out the 2 and multiplying it by 1/4 gives us the 1/2 and everything inside here, so that checks out. Hermitian, take the conjugate transpose. Conjugating this will put the negative sign up here, but then conjugating or transposing it puts this -i up here, then taking the conjugate puts this to a positive, that to a negative, and we get the same thing, so that's a check. And trace, clearly, we see that adding up the diagonal terms gives us 2, divide that by 2 gives us 1, so we're good to go for all our checks. That's pretty helpful. And again, this will help a lot when we get to the mixed states. All right, So pretty quick video, but a necessary one instead of just talking and these, formalisms, giving an actual example of how this stuff is constructed, very important. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. If I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful for each of you for believing in this journey. And if anyone else is interested in joining or supporting this channel, you can join the Patreon community using the link below in the description. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.